Hello everyone, my name is Farzad Tashtarian. I'm going to present our work accepted by Globecom conference. The title of this work is Quality Optimization of Live Streaming Services over HTTP with Reinforcement Learning. We first give a brief introduction and define the problem, and then we explain the details of our proposed approach. And then we take a look over results and followed by the conclusion and future work. Recent years have seen tremendous growth in HTTP adaptive live streaming or live traffic over the internet. And for communicating between the clients and the servers, HTTP adaptive streaming or has become a de facto solution for this purpose to provide the acceptable level of quality of experience. However, due to dynamic network condition and diverse request patterns, we have a large overhead and significant increase in time complexity. Let us explain through the example. Consider the video contribution part that provides segments in different qualities. And these segments should be delivered to the CDN servers at the different geographical location. So by having these segments in the CDN servers, they can serve the requests that are collected from the host players. In fact, host players send a HTTP request for different qualities and different live channels, and then CDN servers can serve them by replying request segments through the HTTP response packets to the clients. However, the problem is how to increase the quality of the experience perceived by the clients regarding different parameters. For example, network bandwidth between users and the CDN servers, or the number of requests for similar channel and quality. And also considering different methods to serve clients, for example, fetch from CDN origin server, or transcoding from the higher quality to lower one, or serving with the lower quality, which should be selected. So let us define the problem as follows. How do we process and serve numerous clients' requests demanding different live channels with various bit rates at the network edge to elevate the client's perceived QE in a network with the adverse bandwidth condition? So here we propose ROPL, that is a learning-based client request management solution at the network edge. Leverage the deep reinforcement learning and serve the request of concurrent user joining and leaving various HTTP live video channels. In fact, and as you can see here, the RVP, that is the main core module in the ROPL, gather our request from the players in its own zone and then select which one should be served with which action or with which method. And let us explain some modules in the RVP. You can see here that host players try to communicate with the CDN or origin server, but here an RVP in this between them plays an important role. For example, here you can see that RVP consists of the different components that Service Manager or SM module enable them to communicate with each other. After gathering requests from host player, SM module send them to bitrate classifier or BC, and the BC classify them in different queues of different channel. And then DRL agent with having bandwidth monitor values that are periodically measured by the BM can decide which request should be served with which method. So we use deep reinforcement learning with the proximal policy optimization or PPO algorithm, that is policy gradient based algorithm, with an action critic approach. And to translate our scenario into the Markov decision process model, we need to consider these steps: a state space, action space, policy, and reward function. For the state space, we provide the observation of a space for the agent through defining this set or OT. That includes the limited number of Rij. That Rij indicates the number of the same request for bitrate J of live channel I, and omega is the available bandwidth given from the SM module. For example, in this figure, you can see that for R11 is 4, and because we have 4 below requests here, R12 is 2 because of the 2 green requests. In some cases, in some scenarios, we have empty requests, or we have empty queues, or 0 request for a specific bitrate. So we can have R13, for example, here equal to 0. For the action space, we define A as a set of actions that can perform by DRL agent, where IIJ indicates the selected action for aggregated requests in the QJ of live channel I. And at each time step, we have this set of the actions that are selected by the DRL agent. In this work, we consider these actions. For example, action 1, that means that DRL agent decide to fetch the requested segment from the CDN origin server, or in action 2, DRL decide to serve the request with the lower bitrate, because the lower bitrate is available in the DRL cache, and DRL then select this segment, select this bitrate to serve clients. And action 3 is serving the request through the transcoding function and producing the requested segment through the transcoding from the higher bitrate. And action number 4 is do nothing, means that there is no specific action for this observation request. For the action, for the policy, policy refers to the logic base on which the agent takes action according to the according to a particular observation. A policy is optimized by learning from the environment and updates based on the reward signals. A desired convergence of policy happens when the agent learns to take the most rewarding action with the highest conditional probability, and a policy update does not change the current one. For the reward function, that is the main component and the undeniable role in the DRL we have to design this reward function that guides the agent toward the following purpose: serving request with the lowest cost and the maximum quality of experience. So our proposed reward function consists of two main parts: serving cost and violation penalty. For the serving cost, regarding the aforementioned actions, action 1 to action 4, we define 4 cost function here, C1 to C4. In C1, we consider the size of segments for fetching action, for the fetch action, that this coefficient regarding the cost of bandwidth for applying action 1, and for action 2, because of serving with the lower quality, lower bitrate, we consider the difference between the bitrates, and also we consider another coefficient value. And for this C3, we also consider a coefficient regarding the cost of computational resources for applying transcoding function, and also we consider time of transcoding. And for action 4, because the URL agent doesn't do anything, so we consider 0 as the total cost for this function, this action. And for the considering the violation, we define 5 constraints that when DRL agent violates each of them, we applied 1 penalty. And these constraints are designed as follows. For example, constraint 1, whenever any action, other action 4 is taken for an empty request, we applied 1 penalty. Or for the constraint 2, for example, when a fetch action is taken but the bandwidth limit is violated, we applied another 1. So we consider these 5 constraints for measuring the violation penalty. And then we introduced this reward function that consists of 2 parts of the normalized total cost and normalize the total penalty in each time step. And we also consider beta as the real value between 0 and 1. After DRL agent provides the actions, we need to consider those actions that violates the constraint, and we have to omit that and repair these actions. So to prevent applying invalid actions on request, we propose a simple and lightweight post-processing algorithm here. For the performance evaluation, we consider the different scenarios, for example, scenario 1 to scenario 6, and with different players and channel and bandwidth range. And we conducted the performance evaluation in 2 modes, simulation and real world. For the simulation, we consider these scenarios, and for the real scenario, for the real world scenario, we developed the RVP in Python to serve the request received from the Godash player, and also we used the EC2 instance, Amazon instance AWS, to run the HTTP origin server at in the Frankfurt zone, and also consider 3 live channels. You can see here that in the simulation part, in the simulation experiment, that the frequency of the violated actions and the selected action, you can see that the number of the accurate action, or those actions that do not violate any constraint, is in the blue, is the most part of the actions. And you can see that here the priority of, because the cost value of the action number 1 is the lowest, so the URL agent tries to just serve the request by applying action number 1 followed by action number 2. And you can see that performance of the reward function, performance of the URL agent, that the reward value goes up dramatically after a limited number of time steps, and the loss values reach to the minimum value at after limited number of time steps. And for the real world experiment, you can see here that for the different number of the for different values of bandwidth, we run ROPL VRP. That is the only we collect request and we gather request and just send one request of similar request. And direct, it means that there is no VRP and all requests should be sent toward the CDN origin server. You can see that ROPL outperforms the other methods. We propose ROPL, that is the reinforcement learning based approach, optimizing HTTP based live streaming, is an age-based mechanisms. When we conducted our experiment in trace-driven simulation and real-world setup, and we showed that ROPL outperformed existing heuristic approach in terms of the QE with a factor up to 3.7, and extending ROPL to support the multiple VRPs